Last time, you watched words learn to talk. A token reached across a sentence, lit up the one other word that mattered, and pulled meaning toward itself. That glowing grid was attention. But one attention head, on its own, does almost nothing useful. So here's what I promise you by the end of this episode. You will see the single repeating piece that, stacked over and over, becomes GPT itself. And you will meet the one tiny screw that holds the whole tower up. Watch this. This GPT. All of it. A glowing tower. Dozens of glassy slabs stacked into the sky. The model that writes essays and code and poetry. It looks impossibly complicated. So let's do something almost rude to it. Let's collapse it. The whole tower telescopes down, slab into slab into slab, until only one is left floating alone. That is the entire secret of this episode in one image. GPT is not 96 clever, different inventions. It is one piece, copy-pasted. So our whole job today is small and strange. We are not going to invent anything new. You already own every part. We are just going to snap them together into one brick and then learn the trick that lets us stack that brick deep, 96 layers deep, without the whole thing falling apart. By the end, you will look at the biggest model on Earth and see, honestly, just one shape, repeated. Let's build the shape. Here are the two parts you already have. On the left, attention, the glowing grid from last time. Its job is to let the tokens talk to each other, so each word can gather context from the rest of the sentence. On the right, the layer of neurons from the very start of this series, the one with the little kink, the fold that bends a flat space into a curve. Its job is to let each token sit alone and think. Attention, the tokens talk. The neuron layer, each token thinks. Talk, then think. That rhythm is the entire block. One quick upgrade to attention before we assemble. A single head is like looking through one lens. It might track which noun a pronoun points at, and nothing else. So we run several lenses at once, side by side, in parallel. One head watches subject and verb. Another watches adjective and noun. Another tracks something we may never be able to name. This is multi-head attention. Run all the lenses, line up their answers, and pass them through one final matrix that glues them back into a single vector for each word. Now let's assemble the brick bottom to top. A row of token vectors flows in from below. First, before anything touches them, we normalize. A quick shimmer passes over the vectors and levels them out so every number sits in the same calm range. Think of it as a sound engineer setting the levels before the band plays, so nobody shouts and nobody whispers. On screen, each vector becomes a tidied version of itself. The numbers are now polite. Now the work can begin. Step 1. Attention runs on those leveled vectors. The grid lights up. Every token reaches out, gathers the context it cares about, and produces an update, a little suggested change to itself. Here is the part to slow down for, because it is the heart of everything. The block does not throw away the original word and replace it with a new one. Instead, it takes the update and adds it back onto the original. The vector you started with keeps flowing straight up, and the attention output merges into it. Add, do not replace. Picture it as a highway. The original meaning of each token drives straight up the road, lane unbroken. Attention is an on-ramp. It does not stop the traffic and rebuild every car from scratch. It just merges a small correction into the lane and lets it keep driving. This unbroken road has a name. It is the residual stream, and that little add we just did is a residual connection. Hold onto that highway. In a few minutes, it is going to save this entire tower's life. Step 2. We level the vectors one more time, and now the other half of the block runs, the neuron layer where each token thinks for itself. And it does it in a very particular shape. First, it expands. Each vector is projected up into a space 4 times wider, suddenly given far more room to spread out. This up projection is where the model has space to compute, and quietly, where a lot of what it knows seems to be stored. Inside that wide space sits the kink from episode 1, the fold. A nonlinearity called GELU in GPT, a close cousin of the old ReLU crease. Without that single bend, this whole expensive layer would collapse into a plain straight line, no matter how wide you made it. The crease is what lets the layer carve a genuine curve out of flat space. It is the same fold you have seen since the beginning of this series, just doing its job in a much bigger room. Then it squeezes back down. A down projection collapses that wide folded space back to the original width, producing one clean update per token. And then, of course, the same move as before, we add that update back onto the highway. A second on-ramp merges in. The token's meaning was never replaced. It was carried straight through and edited twice, once by talking, once by thinking. That is one whole block. And here is the quietly perfect part. Look at the shape of what flows out the top. It is exactly the same shape as what flowed in the bottom. Same number of tokens, same size vectors, which means the output of one block is a legal input to another block. So you can just do it again. And again. And that single fact, same shape in, same shape out, is the entire reason this thing scales. Stack as many as you want. But before we stack, there is one problem we have to solve first. A few episodes ago, I made you a promise and then left it hanging. I said, stack 100 layers, and the signal at the back barely moves. The network goes deaf to its own mistakes. That was not a throwaway line. It was a real wall, and for years it stopped deep networks cold. This is the scene where we finally pay that off. This is the hard part of the whole episode, the bit that trips everyone up. Go slow with me, give me 60 seconds, and the entire trick is going to snap into place. Remember how a network learns, predict, then blame, then nudge. The blame travels backward through every layer, and from episode 0, you know how that blame moves. The chain rule. It multiplies. Layer by layer, the learning signal gets multiplied by another number on its way to the back. So watch a tall plain stack with no highway. A bright dot of flame enters at the top, and at each layer it is multiplied by some factor a little less than 1. Multiply by 0.7, then again, then again. Watch the dot. It dims. By a dozen layers down, it is a faint smudge. By the bottom, it is gone, multiplied into nothing. The first layers of the network never feel the blame at all. They get no signal, so they never learn. The network has gone deaf, exactly as promised. For decades, this is why you simply could not train a very deep stack. Stack more, and it somehow got worse, not better. Now add the residual back in, and watch the math morph on screen. Each block no longer just transforms the vector. It outputs the original plus the change. And when blame flows backward through that plus, calculus does something almost too good to be true. The derivative of the original plus the change comes out as 1 plus the derivative of the change. There is a 1 sitting right there. Let me circle it. That one is the whole ballgame. Because backprop through a plain plus does not shrink anything. It copies the blame straight through undiminished. So the gradient has 2 paths home. The long, winding path through the layer which might fade. And the highway, where it is just multiplied by 1 mile after mile and arrives at full strength. Rerun the backward pass with the highway open. The dot enters at the top, drives down the residual road, and reaches the very first block still blazing bright. Every layer, even the first, finally hears the lesson. Let that land because it is genuinely one of the most important ideas in modern AI. A residual connection is a highway with on-ramps. Forward, the meaning drives straight through and never gets lost in traffic. Backward, the blame drives home without losing a single mile, because adding a number and then undoing it multiplies by exactly 1. 1 screw. Add the input back. That is the whole reason a 96-layer model can be trained at all. And this is not a transformer-only trick. The first time anyone really pulled it off was in image recognition back in 2015 with an idea called residual networks. Before them, the record for a working deep vision network sat around 20 layers. Add more and performance fell off a cliff. Then they added these shortcut connections, and suddenly trained a network over 150 layers deep and won the year's biggest competition. 1 plus sign broke the depth wall. Everything tall in deep learning since then stands on it. One honest footnote, then we move on. That leveling step, the normalization, is the guardrail that keeps the highway safe. As the tower gets tall, the numbers can drift and blow up or fade away. Normalization gently rescales them at each stop, so the additions stay sane. Modern models put it before each sublayer rather than after, which trains far more smoothly. The residual is the highway. The norm is just the guardrail along it. Now, let's open the brick up and see what it is actually made of. Here is the part that surprised me most. Attention gets all the fame. It is in every headline, every diagram, every breathless thread. But attention is the minority of the model. The flashy part is not where most of the brain lives. To see it, we just have to count. and the arithmetic is honest and clean. Let's do it for the biggest GPT, the famous one with 175 billion knobs. Each block's thinking layer has two big matrices, one to expand 4 times wider, one to squeeze back. Multiply out their sizes, and a single block's neuron layer holds a bit over 1 billion knobs. Now stack 96 of them. The thinking layers alone come to roughly 116 billion. The attention layers, all 4 of their matrices across all the blocks, come to only about 60 billion. The bars fill in. Roughly 2/3 of GPT is the plain, unglamorous thinking layer. And here's the part I find genuinely remarkable, told honestly. That wide expanded layer is enormous. In the biggest GPT, it is just under 50,000 units across, per block, and the leading evidence in interpretability research suggests those units behave like a giant key-value memory. That a specific row might fire for the fact that Michael Jordan plays basketball, and another for the capital of France. We are not fully certain, but the evidence points one way. The thinking layer is also, quietly, the memory. The boring 2/3 is where the model seems to keep what it knows. So now you have the whole brick. Normalize, let the tokens talk with attention, add it back onto the highway. Normalize again, let each token think in a wide folded layer, add that back too. Same shape comes out as went in. Talk, think, carried on a highway, leveled at each step. That is a transformer block. And now, finally, the move the whole episode has been driving toward. We stack it. The single block clones upward. 1 copy, 2, 4, the slabs rising into the tower from the very first image, and the residual highway draws itself as one continuous glowing line running from the input at the bottom all the way to the output at the top. Data flows up the road, and each block leans over and writes one small edit onto the stream as it drives past. Talk, think, edit. Talk, think, edit, all the way up. And the only thing that separates the models you have heard of is how many times you press copy. The original transformer back in 2017 stacked 6 of these. GPT-2 stacked 48. The famous big GPT stacks 96. Same brick, same talk then, think rhythm. Same highway, more of it. The numbers cascade up the side of the tower, and you realize the leap from a clever idea to a world-changing model was, structurally, mostly the courage to stack the same thing higher. One careful honesty here, so you are never fooled. The blocks are copy-pasted in shape, not in their settings. Every block has the exact same design, but its own learned weights, its own personality. So it is not literally 96 identical layers doing identical things. It is 96 instances of one design, each tuned a little differently by training. Same brick, different settings. That distinction is the whole truth of it. So, let's close the loop I opened. I promised you the one repeating piece that becomes GPT, and the one screw that holds the tower up. The piece is the block, talk, then think, both wrapped in an add. The screw is that plus sign, the residual, whose derivative is exactly 1, so the learning signal reaches every floor of the tower undimmed. That is it. That is GPT skeleton. One brick, one highway, pressed copy 96 times. Step back and it is almost funny how simple the shape is. The largest models humans have ever built are not a sprawl of 100 different clever machines. They are one honest little machine that talks and then thinks and carries its meaning up a highway, repeated until it fills the sky. The wow was never the size. It was always the simplicity. The size is just the same good idea, refusing to stop. But our beautiful tower has a secret it is hiding from you. For all its 96 floors, it still cannot even read your raw text. Watch. We hand it a sentence, the cat sat, and it has no way in. The tower eats vectors, not letters, so first the words have to be chopped into pieces it can swallow. And worse, even once they are chopped, scramble them, the cat sat versus sat the cat, and the block reacts the exact same way to both. It has no idea what order they came in. So before this tower can do a single useful thing, your raw text has to be turned into pieces and stamped with an order. Chopped and ordered. That is exactly where we go next.